Humans have always looked to the heavens and seen themselves in the stars. Those swirling constellations have inspired epic journeys and fantastic myths and the wisdom of something greater than ourselves. But it wasn't the twinkling points of light that fascinated our next speaker. It was the absences around them. Andrea Ghez is a professor of physics and astronomy who discovered a supermassive black hole at the center of our galaxy. For her work, she became the 4th woman to win the Nobel Prize in physics. She's also the first woman to receive the Crawford Prize, one of the world's most prestigious science prizes. In her work, Dr. Ghez found that the darkness of the universe has as much to teach us as the light. And we're so grateful she's here to share these lessons with us today. Please welcome Distinguished Professor of Physics and Astronomy, Dr. Andrea Ghez.
All right. How do you observe something you can't see? That is an essential question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. The story I'd like to share with you today is how we've been able to discover a supermassive black hole at the center of our galaxy and transform our understanding of the universe. But this is also a story of how UCLA understood the opportunity to invest in a new and emergent field that was a strength of Los Angeles and put itself at a forefront of discovery. I came to UCLA because of the Keck telescopes. These are the largest telescopes in the world, and they are co-owned by the University of California and Caltech. They represent an enormous university investment. $200 million to build, $50,000 a night to run. Tools like these are what put the University of California as one of the leaders in the field of astronomy and astrophysics. They are also why 1 in 5 researchers in this field are at the University of California. We have the best telescopes in the world, which are like modern-day pyramids. This is me. And the program I launched 30 years ago was designed to develop new methods for using these telescopes to find and study black holes. Specifically, the objective was to measure the orbits of stars at the galactic center. While today this program seems obvious, my first proposal 30 years ago was turned down. The review committee did not think our technique would work. And this is when I discovered my favorite expression, which is, every challenge is an opportunity. I had convinced my UCLA colleagues that this was a great idea, but I still had yet to convince my other colleagues that it was. Let's just say that I learned how to make the case, and I gave a lot of talks, and a year later we were off and running on the first 3-year leg of this program. Today, this program has grown into something that is far larger than I could have possibly imagined 30 years ago. We are a core team of 24 people, and we have a collaboration network of about 100 people around the world. And we are answering questions that I simply could not have imagined when we first started. And we are in a leadership position of a $1 billion project. Okay, so what is a black hole? Well, black holes require relatively exotic physics to properly describe them. The way I'd like you to think about a black hole today is that it's an object whose mass is confined to 0 volume. So despite the fact that I'm going to talk to you about objects that are supermassive, they have no finite size. And in physics, anytime you have something that has no finite size, it's like a giant red arrow saying, you do not have your description of physics correct here. The problem is we don't know how to make the field of quantum mechanics, which is the description of physics at small scales, work together with general relativity, which is our best description of gravity. And black holes are certainly small and have strong gravity. This is what makes black holes so interesting to study. They are really at the frontier of our understanding of the physical world. While black holes have no finite size, there is an important size or radius that is associated with them. It's known as the Schwarzschild radius, or the event horizon, as you may know it from Star Trek. This size is important because if an object, and I mean any object, is compressed down to this scale, it will become a black hole. So once an object is confined to the Schwarzschild radius, the object's gravity overcomes all other known forces, and the object will continue to collapse to become the infinitesimally small object and become a black hole. So to prove the existence of a black hole, we must show that an object's mass is confined to within its Schwarzschild radius. Okay, where do we find them? So our theories of how galaxies form suggest that they have a supermassive black hole at their center, and that it regulates the future growth of the galaxy. So if we want to prove that it's correct that black holes reside at the center of galaxy, there's one galaxy that is the best place to study, and that's our own. It is, after all, the closest. So remember, to prove that there's a black hole, we need to show that there's a lot of mass confined to a small volume. To do this, we need to find stars at the center of the galaxy and to be able to measure how they move. Stars will orbit the black hole just like the Earth will orbit the sun. So we are inward bound, and we have the telescopes that should, in principle, be able to see these objects. But the challenge is the Earth's atmosphere. Sure, the atmosphere is good for us. It allows us to survive here on Earth, but it blurs our images of astronomical sources. And you know the saying about how car crashes happen close to home? Well, imagine this. The light that we are studying has been traveling to us for 26,000 years. And in the last 30 microseconds, it hits the top of the atmosphere and suffers tremendous damage. So I've spent much of my career developing techniques for overcoming the distorting effects of the Earth's atmosphere. And by doing this, we've discovered thousands of stars that are at the very heart of our galaxy. So once we could see these stars clearly, we could not only estimate their speeds, which is all we had envisioned doing at the outset of this program, but we could also measure complete orbits, which is a much more powerful approach to measuring enclosed mass. You can probably find my favorite star in the galaxy. It has the very exotic name of SO2. Its orbital period is 16 years. And for context, it takes the sun 200 million years to go around the center of our galaxy. It is truly amazing to be able to see something in our universe that happens on a human timescales. Okay, so before we started this experiment, we knew that there was 4 million times the mass of the sun inside this giant circle. And what this experiment has done for us is to show that that mass is confined to a much smaller volume. Knowing that increased the evidence for a supermassive black hole by a factor of 10 million. So think about anything you would like more of and what it would mean to have a factor of 10 million times more of it. For my kids, without a doubt, this would be their allowance. The advance we have made over the last 30 years has moved the notion of a supermassive black hole from a possibility to a certainty. And it was what was recognized with the Nobel Prize in Physics in 2020. It was awarded to 3 people, a theorist and the leaders of 2 competing teams, including mine. Now, people often ask me, now that you've, are you done? Now that you've won a Nobel Prize. And my answer is always absolutely not. There's so much more to learn. Almost every prediction for what we should have seen around this black hole has been inconsistent with our observations. We have discovered young stars where there should be none. Those are the blue-green stars. We see a dearth of old stars where they should be plentiful. Those are the orange stars. And we have discovered stars that are being destroyed in real time by the black hole. Those are the pink stars. For me, it's like being a kid in a candy shop. There's so much more to be learned. And we are not only not done, but we are advancing the next generation of instrumentation for another decade of discovery. We are pursuing how gravity works and how black holes shape both their host galaxies and the universe. And as we celebrate this next chapter here at UCLA, I can't help but think about the things that this university has made possible. My team was, shall we say, scrappy, not the most established group of luminaries around. And our project didn't seem important to a lot of people. But the University of California and UCLA gave us the tools to look deep into the universe. And we were able to bring something incredible into focus. We showed the world something that's impossible to see directly and discovered more questions than answer. And that's what UCLA does every day. We ask questions. We explore those things still shrouded in darkness. And we bring new knowledge and understanding into focus. And I'm so proud and grateful to be part of this incredible institution. Thank you.